name is Christian Spindler. I'm leading the machine learning and IoT team in PwC, and actually my employer sits really just there. So it was a very, very short trip for me this morning to come here. Hope you enjoyed the conference so far. So I want to show you some thoughts and some experiments we did about the question how to bring trust into artificial intelligence. And the background of this is that we are on a regular basis implementing artificial intelligence projects, building a machine learning pipeline, building a data curation pipeline before them, and doing the software implementation in the end. But then we are also always at this point where we ask ourselves, and the client asks us, are we really developing the right thing? Do we really creating a solution where people trustfully work with the solution? And this is where this talk goes about. Who of you who is currently in the audience knows the Google call at a hairdresser salon? Any of you? Yeah, I see some hands. That's great. Google developed a software that called at a hairdresser, not identifying itself as a software, and still it was a remarkably call. If I'm searching for words and if I'm doing these ers and ams and so on, they programmed it into the software as well, or actually not programmed, they teach the software to behave like this as well. And it was really sounding like a human. You cannot look into what Google really did in order to achieve this, but it was really remarkable. So if I would be at the other side of the phone and some client, some customer calls me and wants to have a time slot for a haircut, it would be interesting to know if this is really a person or not. Not that I would really mind being called by a machine, but I would really like to know if this is a machine calling or not. And this raises a question, do I trust these systems? Should these systems be maybe also regulated to identify themselves and so on? Another example from another big company, the story is with IBM Watson in that case. So you know that IBM Watson was, or one use case was to help doctors to make better therapy predictions, to have a better therapy for their patients. And maybe some of you know the result of some of those experiments, like you can have two outcomes. The one outcome is that the artificial intelligence in form of IBM Watson goes in line with what the doctor's recommendation for a patient was. In that case, there's not so much added value to the patient really, or to the doctor really. The other case is much more interesting, like if the doctor and the artificial intelligence do not have the same opinion in a certain setting. And in that case, it turned out that most doctors did not trust the artificial intelligence. They rather trusted their year-long expertise and their strong education in a certain field. So in the end, in neither of these cases, the artificial intelligence was really bringing a lot of value. And one strong point is that the people were not trusting in the AI. I want to show you a little bit how we can proceed in building trust in AI. And one important aspect, I mentioned it here already, is debiasing data. And I mention it here because the picture you see here is a wonderful example for a biased data set. Who tells you that the doctor has to be male? This robot doctor, it wears a male suit, basically. It looks like male when you look at it. But this is a very biased picture that we have in our minds. And one part of the talk is about debiasing these kinds of data. Now, we're doing this not only for our own interest, because we are seeing there's a lot of risk in artificial intelligence if you do it not in the correct way inherently. And if you look at the slides afterwards, here's some of the risks you see there. This is financial risk, this is performance risk, ethical risk, and many of those things pop up. And I'm not saying that this is a showstopper. You can manage all of those risks either independently or holistically, but it looks a little bit on the side of artificial intelligence that is a little bit off the shiny startups that only promote the nice outcomes. There is actual material risk in artificial intelligence as well. So let's look into some of those risks. And I deliberately go into a small fraction of artificial intelligence, which is computer vision. Now, maybe in the first rows, who of you knows what that is on the screen here? Well, it's a teddy bear. Why? You're good. It's a teddy bear, and actually the human conscious knows this in the instant of a millisecond or so that this is a teddy bear, right? And actually it's also for a computer not a difficult task. It's basically a commodity to have algorithms that tell you that this is a teddy bear. The only thing is the algorithms that we have now, they come up with a solution of, well, this is a teddy bear of 90, because I believe it's a teddy bear of 90% probability. But there are still 10% of probability where I'm not sure as an algorithm. It could also be, it could be an ape, it could be a cat, it could be anything else. This is the result that we're getting from commoditized algorithms in computer vision today. Now, is this developing trust? Even if the number would be 99%, is this really developing trust? I do not think so, because humans are not used to think, to rationalize, to plausibilize things in terms of probabilities. No matter how high this probability will be, we will always have a matter of uncertainty in that. Instead, what we want to have is things like this. We want to have an algorithm that says, okay, this is a teddy bear because I identified the elements in a teddy bear that tell me it's a bear, basically. Yeah, it has round ears, it has brown fur, it has arms, and all of those things, they are working in your mind subconsciously when you identify instantly that this is a bear. Now we want to have explanations of algorithms. This is where it boils down to. Second thing, what we also want to have is a solution to that problem here. It is a solution to biased data. Now this little friend, this little polar bear could really be offended by this algorithm because one of the decision criteria of these algorithms to classify as a teddy bear was that it has brown fur. Now polar bears tend to have not brown fur, so this is really discriminating against polar bears. And this is the second thing, you know, you have biased data set. I told you about the male doctor image in this schematic before, but you have it all over the place, these biases in data. And then lastly, one third thing to the computer vision case, but basically all what I'm telling here is applicable to all of artificial intelligence, machine learning models you have out there, is you can just fool them. On the left-hand side, you can see a teddy bear classified with 99% probability correctly as a bear, right? But then you add to this picture a not really random noise, but a highly engineered noise pattern that I amplified here for you in order to make it visible. Normally it would be a black screen with just some pixels modified there. And then you can fool a classifier such that it now believes it's a totally different thing than a teddy bear. And now imagine this is not a bear, but it's a stop sign in your self-driving car, or it's an investment advice, or whatever you have. But you can fool these algorithms, and they would totally go in a different decision mode as you would like them to have. Those are three problems we need definitely to tackle in order to generate trust in AI. And there's more to that. I thought this is a good summary of things that needs to be done, like exposing people to artificial intelligence in order to make them using it, in order to make them aware of what it is doing, but in same important, what are the limitations of artificial intelligence solutions today? So getting people using it is one solution to generate trust. Then explaining the algorithmic outcomes, you know, the thing with the brown fur and the teddy bear is a second very important thing to me. And the third thing is basically enabling people. It can, in literally all examples I've seen, it can be the case that if you allow people to have their say on algorithmic outcomes and modify maybe the outcomes or the algorithm a little bit, I mean, not in terms of modifying, in terms of coding, you know, I do not want to get all the people to code, but modifying in a sense that people are able to modify algorithmic outcomes so that they take ownership because, you know, you think you did something where you have an own thought process going into. This really helps in building trust. I want to go a little bit more into detail of the thing in the middle, the explanation, because the thing in the middle is the one you can solve with technology. The other two as well, but for the other two, there's also a strong psychological, organizational, and process-oriented component to it. But the middle thing is really something about technology. You have an algorithm, and you want to explain the algorithm. I show you a little bit in the state of the art what we can do today. The benefits of explanations, like what can you do with it? You can empower product development. Think about a robo-advisor. Think about an investment advisor that tells, or robot advisor that tells you should invest into a certain portfolio with 90% probability. You won't trust it. But if you have a solution, an explanation solution that tells you should invest into a certain portfolio because of that and that and that reason, you have a much stronger trust component in there. So product development is strongly benefiting from explanations. Cost saving is also strongly benefiting. When I have an algorithm that tells me I should change my business process to a certain direction in order to save cost, maybe I believe it or not, because this is against my long-year business experience that the algorithm goes against, right? But if the algorithm is explainable and can explain itself, basically, then there's a much higher chance that people who have to live the process and maybe also to change the process are really engaged to do so. Be compliant is just, when I mention GDPR, then I can just move to the other slide, because the GDPR itself has a component in it where it says that algorithmic explainability is a key thing, and people have the right, if an algorithm decided on some business outcome for them, standard example is, do I get a loan or don't I get a loan? Then people have a right to get the decision, the algorithmic decision explained. So being compliant is a definite, would definitely benefit from explanations. And then finally, of course, building an entire AI strategy in your business around going from digitization, using AI technologies and so on. It is only possible when you can explain what algorithms are doing. So how do we do this? I want to kind of drive you a little bit into the concept of local explainability. So that would be very easy. You see these green and the red points on the slide. And this is a classical problem we solve. Every problem can be reduced to that one. It's classifying things into yes or no. Red or green, 1 and 0, you get a loan or you don't get a loan. It's always boiling down to that one. Now, if you create a model like this one here, and this one stands now for all the sorts of complicated models we have in the world, like neural networks, which are highly nonlinear, which can do computer vision, all these things, right? That are not intuitively explainable. So if you do this to your financial problem, to your problem, what you have, then you're asking yourself, how can you explain the outcome of this model? And the concept about local explainability is now the following. If I have a point here, a new client that wants to have a loan, or a new sign on the road where my self-driving car needs to identify what's on that sign, or what does it mean for my driving behavior. So if I want to classify this new data point, then I'm not trying to search for an explanation in the entire picture of red and green dots, but I'm really searching very, very closely to this boundary, to this model that I showed in the white slide here. So I'm really looking, how close is this to this decision boundary, and what can I learn from this closeness? And what can I learn means I approximate this highly nonlinear function that I showed here with some linearity at the total vicinity of this new data point that I want to explain. And this is local explainability. This line, this linear model in gray that I showed here, this is only valid at the vicinity of this new data point I want to explain. This is not valid somewhere else, because it's going steeper and less steep once you move up and down the curve, right? But at the vicinity of the data point, it's somehow valid, and a line is always explainable. I don't go into the math details here, but just believe me, when I draw a line, then I can really straightforwardly explain it, and this is not always possible with these curves and nonlinear functions I had mentioned before. So this is a concept of local explainability, one very strong concept, which was developed already years ago. Like, all these methods are not so new, but really pushed up the research and also business applications since about 2016, and now we see first applications in the market that are using the local explainability for complex models. I show you how this relates a little bit to computer vision, because now you saw red and green dots. I want to show you this is also available for much more complicated problems, like you have it in computer vision. What you see is a picture of some street scene in Zurich with a street light in it. Yeah? And we trained a neural network classifier on recognizing what's in the image. And on this picture, the traffic light was correctly classified with 99.8% probability, right? You see it on the slide. And this is basically status quo that we have. Now with this new explanation technologies, we can go the extra mile and really saying, okay, dear classifier, what triggered you to the decision that this is a traffic light on this picture? And this is what you can see on the right-hand side on the screen. I grayed out all the elements on this picture that do not relate to the traffic light explanation according to the computer vision algorithm, but only left these elements in the picture where the algorithm thought, well, this could lead to the traffic light explanation. And you can see in this case, it was really what was really looking nicely, right? You can see that the large blob of picture that is still left at least contains our red traffic light there. Let's make it a little bit more complicated. This is a picture where you have a different set of arrangements of traffic lights, and you can see that it still really performs well. On the right-hand side, the explanations or the elements in the picture where the algorithm thought, well, this triggers me to say this is a traffic light, really are showing you the traffic lights in the picture. Let's make it still a little bit more complicated. Let's look at this picture here. And this is now a very tricky one, because the traffic light is not more the dominant thing you have in the picture, but it's more the street signs. And well, I mean, the algorithm correctly classified that this picture contains street signs. This is not too bad. It also has at least 17% probability. It says, okay, well, no, that the traffic light is actually the most important thing at the picture. Yeah, this was not a question. This ranking was not a question. We just wanted to say, okay, tell me what you see in the picture. And it found the traffic lights again. But look at the explanations. It's horrible, isn't it? I mean, the explanation for traffic light in that example is really showing you not the traffic lights at all, but it shows you the blacked out component of one of the traffic lights, but with a red part of the picture on top of this traffic light component, right? But it completely misses out the green arrows. And this is interesting because it shows you, first of all, limitations of current explanations of algorithms, but it shows you directly the second topic I had in the beginning, namely the bias in data. We used this algorithm in a pre-trained version, meaning we had this algorithm. It was already capable when we loaded it and employed it at our systems. It was already capable to be fed with images and get a result afterwards. Meaning the data that was trained for the algorithms, it must come from somewhere. And our assumption is, well, you sample data from all over the world, but most of the traffic lights in the world are vertically oriented. Yeah? And hardly any traffic lights are horizontally oriented, meaning you have a biased data set when you only feed pictures of this majority class of vertically oriented traffic lights. So this is a clear example for biased data. And well, the way to cure this, well, first of all, we found it out, which is one important thing. And then the way to cure this is obviously trying to get more images like those here with the traffic lights in the correct dimension. Yeah. And now transfer what you saw here to all of your individual business problems. You certainly won't, at least that's my guess, you won't work on self-driving car on your daily basis, but you may work on similar things that either use machine learning or computer vision, natural language processing. You can find the same augmentation in any of these regimes. A last word maybe on biasing or debiasing, and this is actually a link here at the slide that if you follow that link, it really leads you to a page where it's about this loan case. You know, we have population of customers of a bank. Do they get a loan or don't they get a loan? This was a Google blog, so they made a nice story around it, and I really encourage you to click on that link and play yourself through this website. It takes you some minutes to go into, but then the learning effect is quite tremendous, because the story is like you have an algorithm that decides on loans, and you have a population of two groups, and these two groups are not in the distribution of who pays back a loan or who doesn't pay back a loan. These populations are not equal. So there are in one group more people who are paying back their loan, so they have a higher credit score. And in the other group, there are more people don't paying back a loan, and actually the credit scores are very distinct from each other. So if you look at it, you will figure out it's not a trivial solution what to do there. And the real questions are, if I have an algorithm deciding on that, how should the algorithm kind of decide, if it knows that there are two populations, what to apply for those two populations? There's a number of fairness concepts meant here. Well, max profit is obviously not a fairness concept. It's just maximizing your entire profit, irrespective of any discrimination of people or not. There's a group unaware fairness mode where you just sample or you just give the same amount of loans to both groups, irrespective of your disadvantaging some group because they pay more or more of those groups pay back the loans than the other one. There's a demographic parity where it's slightly different argumentation, but in the sense it's the same thing. You're discriminating one of those two populations, and then they come up with an equal opportunity, which is in their feeling and actually also in mine a very good concept. If you have two different groups, not to discriminate anybody, but still coming close to the max profit target of this loan business here. So I encourage you to go in that one. And actually I want to finish with a citation I found, and I think this resembles quite interestingly the limits of technology to solving the problem of trust in AI. It reads, "It may not be enough for us that machines make right or even ideal judgments. We want those judgments to be made as a result of the same psychological process that causes us to make decisions, emotional reactions and intuitive response that have evolved to many as us distinctively moral creatures." With that, thank you very much.